I will spend the next slides showing a demo using Davis, but I am sure that the process in the with using the software of your preference or the software you have available in your institution will also follow the same procedure. So for this demo, I chose a series of pictures of high-speed pictures that I took in this high-rate experiment that was conducted in a Hopkinson bar. So this was a glass fiber specimen under tensile, and the fibers were all aligned in the 45-degree angle, as you may have guessed right. And I took images. I think this was 400,000 frames per second, but the frame rate doesn't matter. If you were wondering also how the speckle pattern was made, you may want to look at this very nice paper. Where also you will find some recommendations on general recommendations for speckle patterns. You may find brief descriptions on what a good speckle pattern is and general recommendations about, for example, speckle size. Okay, so now to the demo. So this is my series of pictures that I took. So this is the folder that contains all the pictures that I took. I think I should have 180 pictures here. Yes, I have 180 pictures. So when you use Davis, normally you need to create first a workspace, but that is basically, there is nothing but a folder where all your projects are going to be stored. So I will start, I have already a workspace. I simply need to create a new project now. So I say create a new project. I will call it GFRP 45 because this is these specimens were glass fiber reinforced polymer with fibers of 45 degrees. In type of project, I say strain because this is what I want to measure. I want to measure strain. And now I want to import the images that I took with the high-speed camera. The images could have been taken with any other camera. So I click on import. And then I have the choice to choose the source of where the images are, and then I go to my folder and I say select folder, and here I can see that already I'm able to import all these 180 images. I select all, I give a name to this GFRP 45, and this, let's say this was my first specimen, and I say 01. Oh, this is for two cameras. Okay, so this was set up. I think the previous analysis I did was for two cameras. I need to change for one camera. It's just this is the other option. Okay, yeah, for one camera. Okay, all time between images. This is not very relevant, but we can simply add it 0.0025 maybe. I think I'm missing 3 zeros. 1, 2, 3. Okay. 400,000 frames per second, yeah. And then I give a name, GFRP 4501, and then I import all the images. Okay, it's taking a bit because the pictures are in the cloud, but maybe this is a matter of 2 minutes. Yes.
When you import images over two cameras, do you have to split the images over two different folders, or can they all be in the same folder?
Yes, I'm not very experienced with Davis, but the way I've been doing it is that I have to prepare the naming of the images beforehand. I will show it now.
Okay. Okay.
So import for two cameras, you choose this option, this one, and camera one. Now here they tell you a number of cameras. You say two cameras, and then if all the cameras are in the same folder, I'm saying in this case that all the pictures from camera 1 will have a name that ends in _0, and all pictures that come from camera 2 have a file name that ends in _1. So if in the same folder you have a series of image files, that one set ends in this and the other set ends in this, then Davis will automatically recognize which ones came from camera 1 and which ones came from camera 0. Depending on the image acquisition system that you may have used, the naming might be different, or you may have your images in different folders, depending one folder for camera 1, one folder for camera 2. But to analyze it with Davis in particular, I think you would need to rename each series of pictures and put them in the same folder and use this suffix wildcard for the file name. If you took the images with Davis, you will already be in this step, right? You have your project and your image series. You will be like this already if you took the pictures with using Davis. You will start from here.
And sorry again, Gustavo, are you going to show how we insert the calibration into that?
No. So in this demonstration is going to be 2D demonstration. So the only step additional to this for using 3D digital image correlation would be to do the calibration.
Okay.
So for stereo digital image correlation, calibration is a must. You cannot conduct a stereo digital image correlation analysis if you have not done a calibration. So this is something that you must always do before conducting your experiment, and possibly after you finish your test series as well, just in case. For 2D, the calibration becomes important only if you are aiming at measuring displacements. In this case, my objective will be to measure in-plane strains, and therefore conducting the 2D calibration is less important. Okay, so now to conduct the analysis, once I have my series already imported here, I simply go here on strain, click here on strain, and then what I need to do is a procedure called masking. In the masking stage, what we need to do is to tell the software what is our region of interest. So let's say we don't have anything selected yet. We will have some tools for masking. This is also very common in all the different softwares. In this case, a rectangular mask suits very nicely for the purpose. So say this basically will save time, because the software will not spend time analyzing the other regions of the image, but will focus only on this smaller rectangle. So this will optimize the time. Now we need to select the subset size. So at the moment, this is roughly okay. I would say we could go maybe even like this. It could possibly be okay. So I would suggest in this case a subset size of at least 20 pixels. So the way you rules of thumb to choose a subset size is that you may want your subset to be approximately 5 times the size of your speckle. I know that in this case the speckle is of different sizes, but you may have in mind what an average size would be. It is possible to measure the speckle size with mathematical functions as well. Some software, I know Davis does it, I think MatchID does it. They have tools to measure speckle size, but I will omit that step. I think this would be approximately good enough. And then this was for the subset size, and then for step size, Davis by default gives you already a quite good value for step size, normally approximately 1/3 of your subset size. You can see that how it changes proportionally. So it roughly is always 1/3. So if you are using GOM Aramis, for example, possibly it does not have the automatic option. So a good rule of thumb is you choose your step size as 1/3 of your subset size. And if you want to change that in Davis, you can just click here and you can change it by yourself. You can put a step size that is to your preference, but I would advise you just to leave it as 1/3 of your subset size. Okay. Then seeding points. This is also very common across all the other softwares. So normally you choose a point, a region that roughly doesn't change across all the other images. In this case, we have the automatic options for seeding points. So I just leave it automatic, so I don't need to worry about selecting manually a seeding point. But if you are going to select automatically, you select manually. Sorry, you select a point that roughly remains not remains unchanged, but doesn't get destroyed during the test. For example, I wouldn't choose a point that later gets cracked. That would not be a good seeding point. Okay. But in this case, the program will choose it automatically. And then these are the basic settings. I think this is enough to run the analysis. And in this case, I can just start the analysis with a button start, and we will see that already something is happening. Okay, so this was quick, as you could notice, and here I have my experiment. So the color scale is on the right hand side. In this case, it is going from minus 1% to 1%, but this is something that we can change. You can always change the range because it can be misleading sometimes. So I can say, okay, don't go negative, only go to, I don't know, to, for example, 5%, and then it should, okay, maybe 5% was too much. Let's go to 2% or to 1%. We can change also different color scheme, and well, but basically this should give us an idea of the distribution of strains in our experiment. Something that could be useful for you guys when you do your analysis, you may want to get a video to put in your presentations. You right click, export movie, and just like that you could have a movie for your presentations. GFRP. I select this folder. So I say to work here. Subfolder 0101, and then I can export at a given frame rate. I can say 20 frames per second. Export, and in this folder that I created, my movie is going to appear, and this is the movie that I can then put in PowerPoint, for example. What else is relevant? If we want to get data out of it, for example, what is the evolution of strain in the x direction? X direction is the horizontal direction, which is actually the axial direction in this tensile test. Where I go is I have to have my process, my processing results selected. I select this processing result. I click on plot. And then two of the main options that are two of the most common things that you may want to do is going to be to place virtual strain gauges, the first button here, or virtual extensometers. So virtual strain gauge will give you the average data measure on the surface covered by the virtual strain gauge. So basically, I'm going to average all the data that I get over this area, and I will plot it. So I will get the history of strains on this smaller area. So I create that virtual strain gauge. I run. This was just not scale, and this is the scale. So this is the displacement. I want to show strain. Okay, this is the history of strain. So you can see that how it is getting in tension, and then I think it's already breaking at roughly this point when it's reached 0.6, 0.7% only. And this what else we can do? Instead of plotting the x component, I could look at what happens in the y component. Though it's not very relevant, but as expected, the y component goes negative because of Poisson effect. And what else we could do? We go back to x strain here to reset the image limits. And as I mentioned, the other thing that you may want to do instead of placing a strain gauge is to place a virtual extensometer. And this you can do with the second option, add an extensometer. And an extensometer will require us to choose 2 points. It will create a line that starts in the first point, ends in the second point, and then we will be measuring the strains on that line. Not across that line, but on the line that starts in the first point and ends in the second point. So if I click here, I can edit the points manually. If I want to, for some fine adjustment, I could say for 30, and then for the Y position, say I want it to be, I don't know, just for 50. And then just to make it perfectly horizontal, I say 0 degrees as an angle. And that's it. And then again, I press start. And then I should get information on this is the change of the history of changes of distance, but I can choose distance strain. I can choose strain here, and I can have here the history of strains for this line. And you can see already that there is a slight difference with a measure that we got from the virtual strain gauge that was 0. I think we reached somewhere here. So when testing composites, or even sometimes when testing neat polymers, you may find these heterogeneities that are important to take into account when analyzing our data. Right, but now this is not everything. We are just about to end. But I may want to export this as an Excel file that then I could then replot it in Excel, in Origin, in MATLAB, Python, whatever, to make it nicer. So the way to do it is right-click on the plot, export data, and then I choose my folder. My working folder is this GFRP. Oh, sorry. And my working folder is GFRP. Where is GFRP? GFRP, select. My subfolder was 01, and I will call this file GFRP underscore strain gauge. No, this is extensometer 01, and then start. And then inside my subfolder here, I have now a CSV file containing this data related to the extensometer. I paste it here, and I can see that I have information on the time, the distance of that extensometer, the strain of that extensometer. So I could plot, for example, these two columns together, and I should have the history of strains, right? Oh, sorry. I think it will be, I see this column. Oh, yes. There, and this should be the history of strains, which is the same that I had plotted on Davis. It's this one. Okay, and right, I think those are the relevant things that you will want to do when conducting your analysis and when exporting your results. So for 3D, as I mentioned, the only difference is going to be the initial the calibration step at the beginning. But the process will be exactly the same. First, you will need to mask your area of interest. You will select your processing parameters such as subset size, step size, and so on. You run, and then for post-processing, you also have exactly the same options such as virtual strain gauge or virtual extensometer. Okay. Any question?